Most people think of satellites as distant, high-tech objects with little connection to daily life. But the truth is almost the opposite. Satellites are part of the invisible infrastructure that supports modern civilization, much like power grids, roads, and undersea cables. Every time you check weather maps, use turn-by-turn navigation, watch live global events, or send data across continents, there is a strong chance a satellite is involved somewhere in that chain. A satellite, in simple terms, is an object intentionally placed into orbit around a celestial body, usually Earth. Unlike natural satellites like the Moon, artificial satellites are engineered for specific missions. Some are built for communications, others for Earth imaging, science, positioning systems, or military tasks. Their design reflects a constant trade-off between capability and survival. They need enough power, enough reliability, and enough precision to function for years in a harsh environment where repair is often impossible. At a societal level, satellites have shifted from being prestige projects of superpowers to utility platforms for governments, companies, and even universities. This transition matters because it explains why their numbers have surged and why the space around Earth is now both economically vital and increasingly crowded. To understand satellites, you need to understand orbit as controlled falling. A satellite is not floating in place because there is no gravity. Gravity is very much present. The satellite stays up because it is moving sideways fast enough that, as it falls toward Earth, Earth curves away beneath it at the same rate. That balance between forward velocity and gravitational pull creates orbital motion. Reaching that state requires launch systems to provide enormous energy, not just to gain altitude but to gain speed. Height alone does not make an orbit. Velocity does. Once in orbit, satellites may still adjust their path using onboard propulsion, typically chemical thrusters or ion systems. These burns can raise altitude, change inclination, maintain station, or avoid collisions. Orbital mechanics also imposes boundaries. If a satellite is too low, atmospheric drag gradually slows it and causes orbital decay, eventually leading to re-entry. If mission designers want long operational life, they must place satellites high enough, manage drag effects, and reserve fuel for maintenance. So when we talk about a satellite mission, we are really talking about sustained precision over time, not a one-time launch event. Not all orbits are equal, and mission goals determine orbital choice. Low Earth orbit, or LEO, is close to Earth and is widely used because it offers lower launch energy requirements, reduced communication latency, and detailed Earth imaging potential. The trade-off is that satellites move quickly across the sky from the ground perspective, so continuous coverage often requires many spacecraft in coordinated constellations. Geostationary orbit, by contrast, sits much farther out and allows a satellite to appear fixed above one point on Earth's equator. This is ideal for many communication and weather monitoring roles because ground antennas can point steadily without tracking rapid motion. But geostationary placement demands more launch energy and introduces higher signal delay because radio waves travel much farther. Then there are specialized paths like sun-synchronous orbit, which lets imaging satellites pass over areas under similar lighting conditions, improving consistency for comparisons in agriculture, deforestation tracking, or urban growth studies. The key idea is simple: orbit selection is not a technical footnote. It is the core architecture decision that shapes data quality, latency, coverage, spacecraft complexity, and mission economics. A working satellite is more than a camera or antenna in space. It is an integrated system built around a platform often called a satellite bus. The bus includes power generation, thermal control, attitude control, computing, propulsion interfaces, and communications links for command and telemetry. Payloads, such as imaging sensors or communication transponders, ride on top of this core architecture. Standardization has become crucial. Instead of reinventing every subsystem for each mission, many programs use modular bus designs to lower costs and speed development. This trend is especially visible with small satellites and CubeSats, where form factors are standardized and launch access has broadened. Still, even small satellites face difficult engineering constraints. They must tolerate radiation, vacuum, thermal extremes, and vibration during launch. Power usually comes from solar arrays, while some missions use radioisotope systems where sunlight is inadequate. Communication with ground stations depends on transponders and carefully managed frequency resources. In short, satellites are compact ecosystems. They must generate power, maintain orientation, execute software decisions, transmit useful data, and survive hardware stress for years with minimal intervention. Communication satellites are among the clearest examples of orbital utility. At their core, many act as radio relay stations in space. They receive signals from one ground point, process or shift frequency, and retransmit to another location, extending connectivity across oceans, deserts, mountains, and regions where terrestrial infrastructure is sparse or politically fragile. A single communication satellite may carry many transponders, each handling designated bandwidth slices, enabling multiple channels of voice, video, internet, or data traffic. Geostationary communications satellites historically dominated this domain because fixed coverage simplifies user equipment. But newer LEO constellations are changing the equation by reducing latency and expanding broadband availability. This shift reflects a broader design philosophy. Instead of a few expensive, long-lived giants, operators increasingly deploy many smaller nodes with frequent upgrades. For end users, the result is often seamless. You place a call, stream a video, or sync remote systems without seeing the orbital choreography behind it. Yet that hidden choreography is what turns isolated points on Earth into a connected network, especially where ground networks are weak, damaged, or non-existent. Navigation satellites transformed location from uncertainty into a routine service. Systems like GPS rely on multiple satellites transmitting precise timing and orbital data. A receiver on Earth measures signal travel times from several satellites and calculates position through trilateration. The concept sounds simple, but its reliability depends on extreme timing accuracy and predictable orbital geometry. Even tiny clock errors can produce major location mistakes. That is why navigation satellites are engineered with highly stable timing systems and tightly managed control segments on the ground. Their impact goes far beyond map apps. Aviation routes, maritime navigation, logistics timing, financial timestamp synchronization, agriculture machinery guidance, and emergency response all rely on satellite-based positioning and time references. In practical terms, navigation satellites provide both where and when, and modern infrastructure depends on both. The predictability of satellite orbits is central here. Because positions are known in advance with high precision, receivers can solve for their own location quickly. Without that orbital predictability, satellite navigation would not scale into the near-universal utility we now treat as normal. Earth observation satellites turn the planet into a measurable system. From orbit, they can repeatedly monitor weather patterns, ocean behavior, land use change, vegetation health, wildfire progression, ice movement, and infrastructure expansion. Their advantage is broad, consistent coverage at intervals that ground teams alone cannot match. For weather forecasting, satellite data feeds models with cloud dynamics, temperature indicators, moisture patterns, and storm development signatures. For environmental monitoring, multispectral and radar instruments detect changes that are invisible to the naked eye, including shifts in forest density, soil moisture trends, or flood extent beneath cloud cover. For mapping and planning, orbital imagery supports transportation projects, disaster preparedness, and resource management. Importantly, Earth observation is not just about snapshots. It is about time series understanding, seeing how conditions evolve, where trends accelerate, and where interventions are needed. This longitudinal perspective gives governments, researchers, and businesses decision power that is both geographic and temporal. In an era of climate volatility and rapid urbanization, that capability is increasingly strategic rather than optional. Scientific satellites expand human observation beyond atmospheric limits. Space telescopes operate in near-vacuum conditions without atmospheric distortion that blurs many ground-based views. Depending on instrument design, they observe across broad portions of the electromagnetic spectrum, not just visible light. This enables discoveries about distant galaxies, stellar formation, exoplanet atmospheres, and high-energy cosmic events. But science satellites are not limited to deep space astronomy. Some orbit Earth to study magnetospheric behavior, radiation belts, or upper atmosphere interactions. Others orbit bodies like the Moon or Mars, acting as orbiters that map terrain, characterize composition, and relay data from surface assets. There are also missions in more complex orbital arrangements, such as halo or Lissajous trajectories, used to maintain useful observational geometry in multibody gravitational environments. What links all these missions is that orbit creates vantage points impossible to replicate on the ground. Scientific satellites effectively convert space into a laboratory platform, where instruments can run long campaigns under stable conditions and gather datasets that redefine how we model the universe and our own planetary system. Satellites also carry major security and military relevance, which is one reason they are treated as strategic assets. Reconnaissance satellites support imaging intelligence. Signals intelligence platforms monitor electromagnetic activity. Early warning systems can detect launches or other threat indicators. In military planning, satellite support influences communications resilience, navigation reliability, targeting workflows, and command coordination. This concentration of function introduces vulnerability. If key satellite services are disrupted, ripple effects can extend from defense systems into civilian life, including telecom, transport, and finance. Because many capabilities are dual-use, distinctions between civilian and military utility are often blurred. A weather image, for example, can support both disaster preparation and operational planning. This overlap drives policy complexity around norms, transparency, and escalation risk in orbit. It also explains why governments invest heavily in space situational awareness and redundancy. The lesson is not that satellites are inherently militarized tools, but that their central role in modern systems makes them impossible to separate from national security calculations. Orbital infrastructure has become an extension of terrestrial strategic infrastructure. One of the fastest-growing concerns is congestion and debris. As satellite counts rise into the many thousands, especially with large constellations in low Earth orbit, collision risk increases. Debris includes defunct satellites, spent upper stages, and fragments from past breakups or impacts. Even tiny fragments can be dangerous at orbital speeds, where relative velocities are so high that small objects carry destructive kinetic energy. Collision events can generate additional debris, raising the risk of cascading effects that threaten active missions. This is why operators perform conjunction analysis, plan avoidance maneuvers, and increasingly design deorbit strategies for end-of-life disposal. Regulatory and coordination frameworks are evolving, but governance is challenged by the pace of deployment and the number of actors now entering space. Sustainability in orbit is no longer a niche engineering topic. It is a prerequisite for preserving the services economies now depend on. If orbital space becomes too hazardous, communication quality, Earth observation continuity, navigation reliability, and scientific mission viability all suffer. Managing debris is therefore not cleanup theater, it is infrastructure protection. To appreciate current growth, it helps to look backward. The modern satellite era began with Sputnik 1 in 1957, a simple Soviet spacecraft whose impact was mostly symbolic and geopolitical at the time. It proved that artificial objects could be placed into orbit and tracked globally, opening a new strategic and scientific domain. Over decades, missions expanded from demonstration to practical service layers, communications, meteorology, navigation, reconnaissance, and research. What changed recently is scale and tempo. By mid-2025, Earth orbit hosted well over 10,000 satellites, with a large share operated by the United States and substantial fleets from Russia and China as well. Those numbers are not just trivia. They represent a transition from sparse orbital presence to dense orbital infrastructure. As launch costs dropped and standardized designs matured, deployment cycles accelerated. Space became less about occasional flagship missions and more about continuous platform operations. We are now in an era where orbit behaves like a contested, commercialized, and operationally routine environment at the same time. The biggest takeaway is that satellites are no longer optional accessories to modern systems. They are deeply embedded in communication, navigation, environmental monitoring, science, and security. Their benefits are enormous: global connectivity, better forecasting, precision timing, broader scientific visibility, and richer planetary awareness. But those benefits now come with system-level responsibilities: safer orbital traffic management, debris mitigation, resilient architecture, and cooperative governance across nations and private operators. The future of satellite infrastructure will likely depend on balancing speed with stewardship. Rapid deployment can deliver transformative services, especially for underserved regions, but unmanaged growth can degrade the very environment those services rely on. If we treat orbit as a shared operational domain rather than an unlimited frontier, satellites can keep scaling their positive impact. If we ignore sustainability, the costs will appear first as technical failures and eventually as societal disruption. In other words, satellites quietly run modern life, but keeping that quiet reliability demands deliberate choices now, before congestion and dependency outpace coordination. If you found this helpful, please like this video and subscribe for more explainers.